Let's now look at a couple of examples where we'll need to apply the techniques we've learned for both single sum problems and annuities. So in the first example, let's assume we're straight out of college and just started our first job, for which we received a signing bonus of $4,000. We're trying to decide what to do with it, and being the very responsible 22-year-old that we are, we decide to invest it toward a future home purchase. We expect to buy a house in 6 years, and in addition to saving the signing bonus, beginning 3 years from now, we also plan to save $1,500 at the beginning of each month. Both the signing bonus and future monthly savings will earn a 3% annual interest rate, compounded monthly. The question is, if we follow this plan, how much will we have saved after 6 years? So we have two components to analyze. First, we calculate the future value of the $4,000 signing bonus over 6 years, or 72 months, at the 3% annual rate. This is a straightforward single lump sum problem. Second, we calculate the future value of a deferred annuity due consisting of 36 monthly payments of $1,500 beginning 3 years from now and continuing through year 6. Also earning that same 3% rate. So let's begin by calculating the future value of the $4,000 signing bonus. We calculate the future value as $4,000 multiplied by 1 plus 3% divided by 12, because we're compounding monthly, raised to the power of 72 months. This gives us a total of $4,787.79 at the end of 6 years. Now let's turn to the deferred annuity. Because we're making monthly payments at the beginning of each month, this is an annuity due. To solve this with a factor table, we would need an annuity due factor for 36 months at 0.25% per month, which is unlikely to be available. So we'll build this in Excel instead. Here we have a schedule for 36 payment periods with a $1,500 payment made at the beginning of each period. In that schedule, we list 36 periods starting at period 36, since the first payment occurs in 3 years. For each payment, we calculate its future value by treating it as a single lump sum and compounding it forward to month 72. The first payment compounds for 36 periods, the next for 35, and so on down to 1. Summing the future value shows that although we contribute $54,000 over 36 months, the account grows to $56,571.92 by the end of year 6. Now, as we looked at in the last episode, there is a much shorter way to calculate this in Excel using the built-in future value function. If we enter equals FV, the rate is the monthly rate of 0.25%. The number of periods is 36. The payment is $1,500 entered with the opposite sign. The present value is 0, and we specify 1 to indicate payments at the beginning of each period. This produces the same $56,571.92 we calculated manually in the spreadsheet. Now, to determine the total available for a down payment after 6 years, we add the future value of the signing bonus to the future value of the deferred annuity. The signing bonus grew to $4,787.79, and the savings contributions grew to $56,571.92. Together, that gives us approximately $61,360 available at the end of 6 years that we can use as a down payment on a new house. So let's now look at a present value example. Assume a company is issuing bonds with a face value of $100,000 and a 6% coupon rate with coupons paid semi-annually. The bonds mature in 3 years, which means the bond will pay $3,000 twice a year for 3 years, with the first payment occurring in 6 months. And at the end of the third year, the $100,000 face value will be repaid. So let's assume we're an investor who requires a 9% annual return on this bond. The question is, what would we be willing to pay at issuance? This is a present value problem involving both an annuity and a single lump sum. The annuity consists of 6 semi-annual payments of $3,000, and because they occur at the end of each period, it's an ordinary annuity. The lump sum is the $100,000 face value repaid at the end of 6 semi-annual periods. So let's begin with the lump sum. We discount the $100,000 face value using the required 9% annual return. But because coupon payments occur semi-annually, we convert the discount rate to 4.5% per period. Over 3 years, that gives us 6 semi-annual periods. So we calculate the present value as $100,000 divided by 1 plus 9% divided by 2 raised to the power of 6, which equals $76,789.57. Now let's calculate the present value of the ordinary annuity using Excel. We use the present value function with a rate of 4.5% per period, 6 periods, and payments of $3,000 entered as a cash outflow. Because the payments occur at the end of each period, this is an ordinary annuity. So as we can see, the present value of the coupon payments is $15,473.62. Adding this to the discounted face value of $76,789.57 gives us a total bond price of $92,263.19. And that's what we'd be willing to pay for this bond to earn our required 9% annual return. Since the required return of 9% exceeds the bond's 6% coupon rate, the bond must be purchased at a discount in order to earn the required return. Now notice that we could also calculate this bond price in a single Excel formula. Because the annuity is not deferred and the final coupon payment occurs at the same time as the $100,000 face value repayment, we can include the face value as the future value input in the present value function. Doing so discounts both the coupon payments and the principal in one step and produces the same $92,263.19 result. So with that, we've now worked through real-world examples that combine single lump sums and annuities. And as long as we stay grounded in the fundamental compounding and discounting logic, we can combine different types of cash flows to calculate either present or future value. Up to this point, however, all of our examples have involved consistent and orderly payments. In the next episode, we'll begin analyzing cash flows that are less uniform. The good news is that we already have the tools we need. We simply have to apply the same principles to a more irregular situation.